Today we are going to continue our tutorial on the topic of generics. Recently we started to look at a simple set data structure implementation in Golang as an example, and we build it for element types string. Today we will see how you can generalize our implementation to actually reuse the code by using the empty interface type, which is a common solution in Go before the recent release of version 1.18 where generics were introduced. So we're going to take another step towards writing reusable code. And after this tutorial, we will finally look at the generic solution that has been implemented by the Go developers. But for now, let's look at another common form of generalization for code reuse. So jumping right back into our old code base. If you don't have it yet, feel free to check out my recent tutorial or simply download the source code from GitHub. It is linked in my previous tutorial. And we want to quickly recap what we did. We created a new type using a struct, and we found out that a map, which is a very useful built-in data structure in Golang, is pretty well suited for creating a set. So you basically just wrap an internal map where the key type is string because we started to build it for string elements, and the value is bool because we don't really need a value, but bool is the smallest one and it's easily usable as a representation. We always insert true here if an element is actually contained in the set. We can create new sets with this new set function. This is a common way in Go for creating new instances. And we have some methods to actually use the set, like retrieving the size, adding and removing elements. We can check if an element is contained because that is one of the main features of a set data structure. And we also have two interesting methods to convert the elements into a slice and return that, as well as stringer implementation. So this is just a simple method that returns the string representation of the elements in the set. To quickly recap the characteristics of a set, it stores unique elements, so you can add elements that are equal, but only one actual unique element will be stored. So that can be useful in several different use cases where you want to eliminate duplicates. You have a very fast lookup, so the lookup time is basically linear, and you can look up elements very efficiently if they are contained or not, even if you're in a deeply nested loop or something like that. So now we already touched on the topic of why we want to generalize our code in the last tutorial at the end. But to illustrate the need for that, we're going to define a new type. Let's say we not only want to store strings in the set, but maybe another type, and let's make it a bit more interesting than string or an int and create a new struct type address. Inside it we hold a name, a street, both are strings, and a zip code, which is an integer for us for the city reference. So pretty easy to understand, right? Just a very basic representation of an address. Now let's say I want to use that in my test. So I write a test function, test set with type address, and I create a few addresses that I want to add to this set. So I call new set, and we initialize some example addresses using this initializer format, where we say maybe Bob has an address at Water Street 17, and just some dummy data. Then we got Alice, and she lives maybe in this street. And we got Charlie, which lives on the Green Road 13. Like that. And as you can already see, there's a compiler error, invalid operation, operator not defined on new set. And that's because I have a typo here, so I want to declare and initialize. But we still got an error that says cannot use address literal value of type address as string value and argument to new set. That is because our new set function expects strings. And we're going to fix that by switching to the empty interface type. The empty interface is specified as interface and then curly braces without any content. That is a type that I'm going to explain in a minute. Let's just replace the type here. And of course also in our set definition. So now no more errors here, and our test is now a bit more happy. I just said that we are not using the set variable yet, but this call compiles. So one step further. What is the empty interface? The empty interface is an interface type that does not have any restrictions. So we could put any specific type in there. As you may already know from one of my earlier tutorials, interfaces are a form of type specification. You can define them like this, similar to a struct, but they do not contain any fields or implementations. They specify signatures. So for example, we can define that this interface has a string method that is called string, 0 parameters, and returns a string. And now every specific type that wants to implement this interface, meaning it is actually of that interface type when it implements it, needs to have this method with these parameters and this return value. And that is useful to basically place certain restrictions on types, maybe parameters. We can pass around different types to a common functionality just by limiting the restrictions to the things that we actually need. So if I got a function that calls a string on its types, I don't have to define it for maybe an address and a color or bank account separately. And I don't have to duplicate this code, but I can write it once and just call the string method. Because I know any type implementing my interface has to have the string method, and that can be checked by the compiler. Now the empty interface is basically like this. It doesn't have any signature specified. So in a simplified way, it looks like this. So any type actually implements this interface since it doesn't have any restrictions, any signatures. You may know that from other languages as being the most common type. So maybe type object or something similar when you got a class-based language, which goes not, but there is a certain similarity there. So we don't have to define it there. We can just use this built-in definition of interface curly braces without any content. And as you can see, it works here. Now going on with our test, we want to do something similar here, like in the test set strings implementation. So I'm going to check that the size is 3. Let's see if this test actually runs. Call save and call go test. And it is already complaining. Cannot use element as type string and argument to append. Need type assertion. Main go 51. So let's see. 51, that is here. Okay, so we got a compiler error. The problem is that the program does not compile. It's not our test itself, but we overlooked it. So since we changed the type in the map to the empty interface, some code that we implemented in our last tutorial video may not compile because it relies on the fact that the type is a string. And I can do certain things with strings, like, for example, concatenate them or print them, that I cannot do with the empty interface type because, as I said, it does not have any guarantees about what the specific type can do and cannot do. So here we got the error, cannot use element to append, need type assertion. So append itself wants a specific type. And by using a type assertion, we can check what the specific type of the interface is at runtime. In this case, we created a string slice here, and we want to append to that. Now we can't do that if we are not sure that this is actually a string. So instead of using a type assertion here, we're going to use the assertion later. We can adapt it to actually use the empty interface. And of course, this also means we need to adapt the return value. And it will have an effect on our string method because it uses a sort function that it expects strings and cannot handle the empty interface. So for now, we can't really implement that because we don't know how to sort the common type. So just for the moment being, I'm going to put this in comments so we can focus on the other methods first. And that means we have to temporarily deactivate these in the test. But except for that method, we switch to interface. And since we're already at it, we can also do the same for the add method, as well as remove and contains. So now maybe let's search for string. Where is string defined? Okay, we deactivated that. And that's our new type. Okay, so we replaced the other string occurrences with the empty interface. Let's see what our test says. Now we shouldn't get any more compile errors. And as you can see, we still have them, but this time in our test. So here we're calling set.string, and string is not implemented. Okay, so I deactivated the wrong call. We have to switch that around. And now it's complaining, okay, set.slice, value of type slice with elements empty interface. To check contains. Okay, so our test helper is probably not prepared to deal with string elements. And we can change that here too. So we're going to switch to the most common type. And of course our expected also need to be different if we want to use this check in our address test too. But I can do that. I can use the empty interface. It will use the equals operator on the specific type. And it will also verify the value. So one thing to keep in mind, again, refer to my video about interfaces and methods. An interface contains a specific value type. This can be string, for example, or address in our case. And it contains the value itself. So the specific value type, which is then address, string, int, and so on, and the value like the actual fields that provide an address of the string itself. So that is why sometimes you can have two equal values, but if the specific types do not match, then this equality check will fail. So that's just something to keep in mind on the side. Now let's try to run our test again, and it runs and it passes. But we didn't yet do much in our test set address case. So we are going to do something similar like in the string case. Let's check some addresses. And of course, the set should contain Bob's address. I'm going to recreate it here. It, like this, should also contain the address of Alice. And Charlie, of course. But it should not contain some address that we didn't really enter, like maybe Zoe. And yeah. that's basically very similar. Now we can test the slice function. And that will check if the conversion to a slice works. Let's see if it works. Don't forget to save and run the test. Yeah, so as you can see, the slice also works with the empty interface element. And the same goes for contains. We can just look up the existence in our map. Every element that we insert gets the value true assigned. That is why we can just return the value of the map. What else do we have? Now the next step is to add an element that is not yet contained. So we will use Zoe for that and see if that works as expected. Size should increase because it's a new element that is not yet contained. And she should be in there now. Again, the slice should now change and have one more element, which is Zoe. And let's verify that. Yes, it works. Finally, we try to add an element that is already contained. So maybe we use Charlie. And that shouldn't change the size at all because it's already in there. Works. Now we're going to remove an element. Let's remove Bob here. So size should decrease by 1. And what is contained? Everybody except Bob. So just to make sure our test works, let's check it first. And yeah, it fails. Expected to find Bob, but slice is like this. So we have to remove Bob because we no longer expect him. In fact, we just removed its address. And finally, we try to remove him again, which shouldn't change anything because the address of Bob is no longer contained. So the size should stay the same, right? That works as expected. Okay, so as you can see here in this little example, switching to the empty interface works pretty well for putting any element inside there. So what is the actual disadvantage of doing it like that? Well, we already touched on that. You can't really make any safe assumptions about the specific types in there. So let's say we want to print some addresses. For example, we could get the slice we say set.slice, and we iterate over it. So I will call it address in range set slice. So what type is address? Well, first is the index. We're going to ignore that with the underscore character. Second is the element type. And as you can see here in the hint, it is the empty interface. So we can't make any assumptions. Maybe in my code, I want to print the address like this. But I can't do that because there are no restrictions on the type. The compiler has no way of verifying that this is actually an address type element. So when I try to run it, it says address name undefined, type interface has no field or method name. And that will happen for every assumption that you try to make. So as you can see, this doesn't work. It works for putting elements inside here and for adding and removing and so on. But once I need to rely on certain characteristics of the specific type, I do not have any guarantees from the compiler, so I can't even write it here because it's not type safe. Now there is one way around it, and this is type assertion, which is basically a check for the specific type at runtime. Maybe you know that from other languages, where it's also called type checks and type casts. In Go, it's called a type assertion, and it looks like this. You can say address dot, and then using parentheses, we want this to be asserted as type address. Then I can assign it, and let's actually call this here element. We're going to assign it to the variable address. And that's my type assertion. Now I can make assumptions on the type. So what I basically did is I told the compiler, hey, I'm sure that is the specific type, and let me use the characteristics of that type. So actually convincing the compiler that you're sure what you're doing and that this is actually an address type. Let's see if that works. We forgot the new line. \n. And yes, it does. So this is the address that is printed. Now we might be asking, well, what's the problem? I can always use these type assertions and it works perfectly. Well, in our little program, it's pretty simple for this use case, but real world programs are pretty complex. And you may not be that sure that it actually contains only addresses. For example, let's just assume we have some other functionality in the program that we didn't see, or maybe a bug or something like that. And we will just add an element here which is not an address, but it could be an integer like 42. Let's see what happens. It crashes. It produces a runtime panic, which is basically a program crash. It says interface conversion is int, not main.address. That actually terminates your program with an error, which can be a serious problem in real-world programs that are important to run. So this type assertion is actually pretty unsafe. You're losing type safety at this place, and you need to convince the compiler with your responsibility that this is actually the type that you want. There's one way to make it a bit more safe, and that is to actually check if the type assertion worked. This is done by using a second return value, because the type assertion returns the converted type if it worked, and the boolean to check if it did actually work. So if I omit that, it will crash, cause a runtime panic when the type assertion didn't work. I can write it in a more careful way and actually use this second return value. If that worked out, I can print it. If it didn't, for whatever reason, I can do something different or nothing at all. So in this case, we are going to say element is not an address, but something different. Yeah. And that is actually executed here, and these type assertions here work. You can also have a look at the address here. And as you can see, this won't yield any reasonable value because the assertion didn't work out. So it's basically the default values of the struct field. So for the name and the address, there are empty strings in here, which are separated by a blank. That's why there are two blanks. And the 0 is the default value for the zip code. So it's just giving you the empty element, as you might say. So this can actually work if you know which types are possible and how you can handle them. But you may also realize that you have to write quite some type assertions and checks and extra code for handling all these different specific types. So it is a little bit more error prone. It somewhat circumvents type safety, which is a very useful feature that the compiler can give us. But it is doable. And we've also seen that you can add mixed types since there are no restrictions on the element type. Specific element types can be mixed, which is often not wanted. I mean, you could have a program where you want to mix element types in a single data structure like set, but usually that's not the case. You want to avoid that, and the compiler can't really help you there. So for example, let's say I wanted to add strings, and yeah, maybe in this program here, I want to add strings. I want to use it for strings only, but I actually did a mistake, and yeah, instead of adding the string one, I forgot to write the quotes, double quotes, and the compiler cannot help me in this case because I didn't say I want these types only. I told him you can use any specific type, and then my other test will fail too, and I'm not really sure why until I dig into it really deep. So mixing element types in a single data structure, probably most of the time not a good idea. So we actually covered quite a lot. Now what we still got to do is this string method down here. So if we want this to work, we actually have to use some kind of restriction or implement some kind of sorting for address. So here we're using the built-in sort, not really built-in, but standard library sort function for string slices. And we can't really use that for address types. So we need a way to actually make this compatible. And one way to do that is by actually making sure that we can convert it to a string. So one idea would be to implement set type assertion and then call the string function on it to convert it. So we can write it like this. We will check the specific type. So first we are reusing the slice method, right? Which gives us all unique elements in the map as a slice. And then we sorted them. But now let's actually check the type of our elements. So we can say create a new slice of strings instead. So we can do it like this. Like this. And then we are going to iterate our elements. So for every element in our internal map, we are interested in the keys, so we need the first return value and we can ignore the other, which is a Boolean. Now we need our type assertion. So if element or let's do this first. And we can now, instead of using this type assertion that I've shown here, we actually want to check for multiple types. We can do that by using a switch case statement. And I've shown the switch statement in one of my earlier tutorials. We can combine that with the type assertion, which is very handy. So I'm going to write a switch on the element. And I believe it's like this dot type. And then I can say case string and do something about. So actually it's not like this. But like that. So this is a type switch. Instead of specifying the type that we want to do the type assertion for, we use type in parentheses, and then you can specify the different cases. So if it is a string type, do this. If it is an address type, do this. And we will add a default that doesn't do anything really, except for printing a warning, maybe stating that cannot convert to string. So we need printf here for the placeholder and add a new line. So if it's a string, it's pretty straightforward. We can just say slice append the element. And as you can see here, it's saying cannot use this as string value and argument, need type assertion. And here we can actually do this because we know the type matches. We checked it before. Now for address, we need to make sure that it's converted into a string. So first let's write a stringer interface implementation for address. It's pretty simple. We can just add the method string, returning a string, and then we're going to use fmt dot as printf, and I'm going to keep it short and just say state the name, then the street and the zip separated by commas. So a.name, a.street, a.zip. That's our string implementation, and since we checked for the specific type, we can easily use that by making the type assertion to address. And of course we still need a string and not an address, so we need to call string on the address. So that's pretty clear, right? We checked that the type is address, and in case it is address, we can be sure that we have a string method to call. And we added the default case. We could also omit it and just basically swallow the unknown type element, but it's usually a good idea to have some kind of warning or info about it. And we just use our string sort and we return it concatenated. Let's see if this actually works. First, we're going to reactivate the string version. And see what happens. And it passes again in its complete form. Nice. So let's do the same for our address. Check string is called here. I'm actually going to do this once only. That's sufficient for our case. And we're going to do this at the end. So here before adding the 42. We will check that this returns a string. And let's see, because we used commas, it could become a bit difficult because commas are also used here to separate elements. So that's a bit unfortunate. Let's make this better. We are just going to use this pipe here as a separator maybe. Okay. So that's going to be in alphabetical order. So first Alice, just like this. So Alice. Then comes not Bob, because Bob is no longer in there. Charlie. Since it's a pretty long string, let's make a line break in there. We can concatenate strings by using the plus operator. So I'm going to write it in multiple lines. And the third one is Zoe. Have to make sure to get rid of the extra quotes here, because it's one string in total. So that's it. The elements formatted using the string method, separated by commas. So let's see if we got it right. And it fails. Let's see why. Alice. Charlie, Zoe. That looks pretty good, but we missed something, I guess. Okay, so the separator here didn't replace it with the pipe symbol. And it passes. So as you can see, we also managed to implement the string method, but due to the missing restrictions that we can rely on the specific element type, we have to add quite some code here to make this distinction, and it's also a bit error prone. So maybe I got a type that I added recently to use with the set, and I forgot to adapt this. So this can easily happen. Let's say I write a new functionality in my program where I want to add maybe telephone numbers to the set, or let's say I want to add some, maybe just integers, and it won't really work. So in this case here, when I had an integer or some other type where we forgot to implement it, because we don't have to make any changes for the other methods to work, but it can easily happen to forget to extend that. Then we got a little problem here, and it says, yeah, cannot convert to string. So we got this warning at least, but you may not realize that, you may not note that at an earlier stage, and the program runs in production and some user finds out that it doesn't really work. And ideally you want to find that earlier. In the outcome we then got 3 elements, although we added another element that we didn't handle here. Okay, I think that is pretty much it. Let's have a look at the README. We learned that we can use the empty interface to reuse code, because we really don't want to duplicate all this code for every single element type that we want to use. That is going to become maintenance hell. It may be fine for 2 types if you don't touch it very often, but usually the more general your code is, like say more generic algorithms or data structures especially, you don't want to go into crazy copy and paste mode. It is very easy to miss something, to make mistakes. If I add a new method to my data structure, I have to add it for every specific copied implementation. This is not a good idea usually. So we want to make sure that we can do code reuse. The empty interface type is the most common type in Golang. It is implemented by every specific type because it has no restrictions at all. So you can use it with any specific type. The downside is you cannot make any type-safe assumptions. That is why the compiler cannot help you. You can make type assertions, but it is somewhat error-prone if you're not careful, and it requires additional code that may become a maintenance issue itself, like we've seen here. You can also mix element types when there are no restrictions, and more often than not, you don't really want that. But to sum this up, this is still a valid solution, and for some cases maybe a good idea. Since generics were only introduced in Go 118 in March 2022, you will also find quite some code bases out there where this is the common norm and still in place. So it's important to understand this approach, the pros and cons. We have also seen that we can use type switches as a combination of the switch case element and type assertions to create complex distinctions for specific types. This is something that you will also find in quite some libraries that do things based on the specific type. So that is it. I hope you liked it and you learned something from it. If you want me to make more of these videos, please let me know. Also, let me know if you want to learn about different things or want me to talk about other topics. I'm open to that too. See you next time when we are going to finally look at the generics in Golang.